You guys haven't had elimination yet in lecture and stuff. And even for the subject of elimination, these are kind of advanced, you know, so don't worry about it if it's, okay. Any questions? Are you kind of getting it now? Any carbocation? Get a carbocation, do a thorough job of looking for all the adjacent protons. Okay. All right. We good? Can I erase? All right, I want to talk a little bit about how we are going to identify what products you have and how we're going to know how much. Okay? Basically, what I want to describe is a very basic view, and Dr. Organ has talked about GC, right? GCMS and stuff, yeah?
No, not yet.
He thinks he has.
Wait, have we done it? We haven't read about it or lectured on it yet. I think we're starting tomorrow.
Where?
Or Thursday. Because it's not on this exam module, we're taking the exam on Friday, Saturday.
Okay.
So you might be starting it this week.
I think he's going to start it.
Yeah.
But
Mass spec? Mass spec?
We've done mass spec.
Oh, okay. That's what I'm thinking. My bad. Mass spec. Okay.
I feel that's on our yeah.
You're right. NMR and IR.
Okay. All right, so determining product identity component. Gas, chromatography. Remember, anytime you invoke the word chromatography, that's separating mixtures, and that's what you guys have. You have a mixture. I gave you some expected, some unexpected, and there's probably some unexpected unexpecteds. Okay, so you need to separate those out and try to pinpoint, you know, at least some of them, what's in them. All right. I'm going to draw a schematic of how a GC works. It's very crude, okay? So, oversimplified, for sure. Okay. We have everything is heated. It's often heated in a ramped type of way. So it starts out, you know, room temp and then ramped. And that ramp is often very specific on how it, you know, a degree per minute type of thing, kind of a melting point apparatus. All right. You will have your sample dissolved in another solvent. It's going to be dissolved today primarily in chloroform, okay? With a little bit of acetone in there. The acetone is actually just serves a little convenient purpose, which I will explain to you in a minute. But you have an injection port. In the most traditional setup, you have a syringe, okay, and you'll inject a small amount, a very small amount of your very dilute sample. I mean, it's just sort of amazing how sensitive something like a GCMS is, okay? And you'll inject it in here. I'm going to say this is in an oven. And then I'm going to draw what's known as the column. In truth, the column is actually within the oven as well, but now, this column, I'm drawing this huge blow-up so I can show you how it works. The column is, I was trying to come up with a good analogy. I'm a cat person. You guys ever picked up a cat whisker or messed with your cat, grabbing its whisker?
Why would you do that to your cat?
Because she's playful. She likes it.
Well,
Well, Stitchy likes it. Lilo ain't playing like that. Lilo's gonna disappear. Okay, anyway, enough of my cat. It's about this thing that I'm drawing. This is called the column, and I'm going to draw like the coating in the column. It's amazing. The column is probably the thickness of a cat whisker. Okay. All right. The coating or the column has a coating. Okay. I forget what it's made out of. And there's different columns that have different coatings. Some type of polymer. And then we got a detector. And detector's vague, and I'm leaving it purposefully vague. There's lots of ways you can detect. You can have something over here that's looking for UV absorption. That would be great if your molecules had lots of alternating double bonds. But not really good for ours here because we don't have alternating double bonds. We just have one double bond. Okay? You can have something over here that actually burns, is just burning anything that comes through. Okay? The one upstairs, actually, what it does is it just every instant is taking a mass spec. So it's actually using a mass spec as the detector. But we don't need to wrap our brains around that part right now. We can just say there's something here that tells us when something comes through the column. Comes through the column. Okay? We have what I'll call a carrier gas. Helium. And so what happens is you inject into the oven, all right? Your product mixture vaporizes, okay? So it goes into the vapor phase, and then gets caught up in this stream of helium that's brushing through, okay? And so your product comes in here, your product starts going in here, but then it'll end up getting absorbed in this coating. Well, I can't remember what coating
Is it absorbed or adsorbed with a D? Because I think there is a difference.
Absorbed.
Absorbed.
Yes, well, absorbed. Yeah.
Sorry.
It's okay. B. Absorbed. Okay. And then, so it gets absorbed. But then, remember, this is all heated as well. It's actually within the oven itself, but heated. So this dude re-evaporates. Gets caught up in the stream, gets going, boom. Gets caught down in there again. Caught up in the stream, evaporate, caught up in the stream, like that until finally it escapes the tunnel and makes it into the detector. That's basically the, an oversimplification of the principle. All right? But you start out here with a mixture, they come in, and going through this process, they're going to get separated out. Okay? So that your different products arrive at the detector at different times. Okay? What physical property do you think is going to dictate whether it comes through here quick or comes through here a little bit slower?
Polarity.
Indirectly, but more directly? Indirectly.
Charge.
What does when we're talking about evaporation,
Boiling point.
now you guys are firing on all pistons.
20 questions.
I like it. Okay, so boiling point. Yeah. So the things that have a higher boiling point, is that going to take longer or shorter? Longer. Yeah. The time that it takes to go from here to here is called the retention time. It makes sense actually. How long it's retained on the column. So those things with a higher boiling point are going to have a higher retention time. They're stuck in the column longer. Those things with a lower boiling point, shorter retention time. Make sense? Beautiful. Okay. All right. Now, what you can do is you can, you're going to get a chromatograph. Here is intensity. And here is retention time. In minutes. And so what you tend to get is you tend to get stuff like this. Okay? And when you shoot something in and you collect a chromatograph, that's called a run. You did a run. All right? So let's call this our standards run. All right? And let's say this is, aha! And don't hold me to this. I don't know that this one comes, I don't even remember. So don't hold me to this, but this is the general principle. Let's say this is minute 2.56, all right? Yeah, shucks. I'm so sorry. That's a weird way to run your standards. You should run your standards one at a time. Okay? So we know what we put in here. Standard runs with 1 methylcyclohexene. That's what's going to happen. That part is done when you guys aren't at the machine. Okay? We have purchased these standards. Okay, 1-methyl, 3-methyl, 4-methyl cyclohexenes, the affiliates, all that stuff. Yeah. You shoot it in so that you know what's going in there, and then you record the retention time. Okay? Aha! So 1-methylcyclohexene comes at 2.56. Then you do it for 3-methylcyclohexene. Okay? And that might have a slightly different retention time. Okay? And you guys will get a document that has all those. Here's the retention times for the different types of components. Okay? And surprisingly, retention times, as long as, remember I said you ramp the temperature? Okay, you ramp the temperature. As long as you're pretty consistent about how you ramp the temperature, the retention times are pretty consistent. Okay? Interestingly, they're not consistent enough year to year. So we can't use last year's retention times. Who knows why? The machine has been used a lot, you know, it has changed, etc. So they will probably run their standards, you know, today, and those will be good for all the runs that we do for all the sections of this class all week. And then you do your product mixture run. Okay? say that this is 2.55, okay? And then this is 3.12, and then this is 5.64. Okay? Don't be thrown if something is, you know, to the hundredth place off from a standard. That would be a safe assignment. Okay, yeah, that was 256. It's 255. That's close enough to assign it to 1-methylcyclohexene. If it differs by a lot more than that, then not a terribly safe assignment. Okay. Notice I made my bumps bigger. Okay. You will also get a readout 2.55, and then you'll have the integration. And maybe your integration will be 46,309. They're kind of big numbers. Okay. I don't know this, but my guess is it's like pixels. Okay? It's like little dots. Integration means exactly what it means in calculus, assuming you guys have perhaps had it. Probably have by now. Has anybody not had calculus? I don't have a sense. It's okay if you have. Everybody had calculus. Okay, so integration here means the same thing integration does in calculus. Area under the curve. Okay? There's your curve. What's the area? That's the area. All right. And then 3.12, 5.64. This is clearly much bigger, so that's 75,3921. Magnitude is 75622.
Were you just making those numbers up?
No, that's what they are. I do that with my eye. I can integrate. It's kind of weird. Since I was a kid.
I just didn't.
Want to say it again?
No.
Yes, I was just making those up. But I made them up so that the biggest one was the biggest. Yeah.
Because I was just going to say that. I was like, that's really impressive that you memorized these for your test numbers.
No, just BSing.
Sounds very sure.
BSing on the spot. That I am actually good at. No. Okay. All right. So that's how it works. Does that make sense? That's how you're going to identify yourself. You'll get a readout for your product mixture. Assign it to what you think, you know, some of the components you may not be able to assign. If you have one that's kind of way out here, sometimes that's unreacted alcohol. Somehow it made its way up into the Hickman head, and it's in there. And it makes sense that an alcohol would have a much longer retention time, right? Because it has a much higher boiling point. Huh? All right. I want to talk about how you guys are going to prepare your samples. All stuff. Okay. And I have procedures if you guys don't have. You're going to start out by putting 90 microliters of acetone in here. Okay? And it's all on this procedure. You're then going to use the fancy auto pipetters, and you're going to take 10 microliters of your product mixture, which is where you left it. It was in the refrigerator over the time. You're going to take 10 microliters of your stuff, and you're going to put it under water. If you'll excuse, there's not water, it's acetone. You're going to put the tip of it under the surface of the acetone and squirt it in. Okay? The acetone, we don't want to analyze it, anything like that. Does anybody have any idea why we use the acetone? Why don't we just take 10 microliters and just squirt it into here? No, because we're going to dilute it in a second with chloroform.
So it can become a gas easier?
The opposite, so it doesn't become a gas. If I put 10 microliters in here, by the time I come over here, it's gone. it evaporated. 10 microliters is an absurdly small quantity. So you put it in the acetone and it sort of gets captured inside the acetone so it doesn't evaporate. Then you're going to add 1.5 mils of chloroform, okay? And sorry, brain freeze. All right. Now what you have to do is we have to run it through a small column, and this is going to be very similar to what you did when you created a column filter. Okay. We're going to run it through a powder called silica gel. Okay, it's the same stuff that's coated on silica gel. Is wonderful stuff. It's in your brand new tennis shoes that you buy. It says "Don't eat," and it's we use it for TLCs. We can use it here. What we're using it for here is mainly to capture any acid that might have made its way into your product mixture. You had a very acidic mixture there, phosphoric and sulfuric. And acid can be rough on this column. So we want to get the acid out of it. So we put in a tiny bit of cotton, okay? A nerd size of cotton. Stuff it down there with this dude, all right? And then in the instructions, I say something like 1/3 of a teaspoon, just because it's a visual thing. Probably a better visual thing is you want about 1 inch of silica gel. Inch and a half. That's a better visual. I should change that. Okay? I also say roll up some weighing paper to create a makeshift funnel. Yeah, it's not the greatest. What I did is I took one of these funnels, I'll tell the lab staff, and I cut off the slanted tip. So now it doesn't fit inside, but it fits right over. So if you use your fingers, silica gel isn't dangerous or anything. I mean, don't, throw it up into your face like snow. But that'll sit over there, hold your fingers on it, and then with a scupula, which I'll get, give yourself about 1 inch to 1.5 inches. Okay? And then you're simply going to somebody got the drawer open? Spatula. Beautiful. Okay. Was it you who didn't have a partner? Who didn't have a partner last week? You did, okay. Maybe you.
Yeah, I'm gonna share with her.
Okay, perfect. And we will get you some product. Which one did you do?
2-methylcyclohexenes.
2-methyl. So we need somebody that has a bunch of 4 that can lend something to each. Okay? All right. Okay, so silica gel. Fashion funnel here. All right, good enough. More than enough. All right. Okay. All right. Now I've got my mixture. I've got my mixture of my 90 of acetone, 10 microliters of my stuff, and then 1.5 mils of chloroform. Okay? You get one of these small little vials, these special vials that go into the GCMS. I should have mentioned You don't get to do this part. A robot is going to do it. A little arm is going to go.
I'm just so excited.
It doesn't make the cool noises that I make. Yeah. This beaker is too big. You have a smaller one. But in any case, you want a beaker in there so it don't spill as always. On this vial down here, you can't put tape on these little vials. It won't fit into the machine. Okay, so you have to take a Sharpie and write on it. Okay, and you're going to write. I put it in there. It's either 2-hex or 4-hex, whether you, depending on which alcohol you started on. Okay, and now I get another pipette. I've got my stuff in here. Okay, and I'm going to start pipetting it through the silica gel. The silica gel will grab all the acid, okay, and it'll go down into this vial here. All right. What'll happen is it'll puddle up here, and it'll go drip, drip, drip. Okay. If you want it to go faster, you can do it in about 10 minutes, or you can do it in about 10 seconds. Should you wish to opt for the 10-second plan, fill this dude up, okay, with your stuff. Drip, drip. Take one of these guys here, a pipette bowl, put it over there, just give it a push. Boom, done. Okay. Does that make sense, guys? Now, all chloroform stuff has to be done in the hoods. We've got 4 hoods, that means 4 people at a time can do it. In a second, I'm going to come up with an order of when we're going, okay? And then we'll let those folks go. And if you may just have to study a little OChem while you're waiting.
Wait, does this have to be done under the hood?
This has to be done in the hood. Yeah, this part, so you're going to build this apparatus and everything, take it into the hood, and do this part, okay?
Oh, the filtering part?
The filtering part, yeah.
Oh,
Yeah,
okay. Okay.
yeah, yeah. Chloroform is a carcinogen. It's a mild carcinogen, but nonetheless, it's a carcinogen, so we want to take precautions.
So do we make the apparatus in the hood when we're adding the chloroform and everything?
You make the apparatus any place, but as soon as you're involving chloroform, don't take chloroform onto your desks. Area. Does that make sense? I forgot to check that, so. Okay, that's it, guys. Any questions? Sorry.
Are these the handouts for today?
Yes.
Okay.